with vaccines. Please,
yeah. Thanks, Hans. I'd like to thank the organizers for inviting me, and it's really wonderful to be back here after 20 years. And I'm not going to prove Fermat's last theorem right now, but that was one of the great exciting things that was going on 20 years ago here. Instead, I'm going to talk about mathematical models for the control of infectious diseases with vaccines. And I got confused. Now I realize I should have had more statistics, but we'll start with some statistics. So I threw this in at the last moment, realizing that I had gotten confused. So what I'm going to do today is I'm going to start just introducing a stochastic model for vaccine efficacy that was born by myself and others. Betsy Halloran, who's here, and during the experience 20 years ago. And then rather than go through the theory of how to model vaccine effects and their impact, I'm going to go through a fairly detailed example, which kind of is a good tour de force of everything. And it's going to be modeling dengue transmission, the coming dengue vaccines, and models for strategies to use as vaccines. But I do want to mention, over the years, we've worked a lot with vaccines and mathematical modeling, statistical modeling of vaccines for a whole host of agents, a number of which I've listed here. So I want to just say a word, although later in the week, Betsy Halloran's going to describe in a lot of detail vaccine studies and their statistics and design. But I just want to mention a few things before we get started. And that is that vaccines have direct effects in that they protect vaccinated people directly, the people who are vaccinated, and they have important indirect effects. And of course, that's where the models come in, and they're very important. And those are the effects of on even unvaccinated people, the widespread effects of vaccination on people who are not vaccinated. And then total effects, taking into account the fact that vaccinated people not only are directly protected, but also indirectly protected in the population. And then overall effects, which talks about the fact that just pick a randomly selected person, whether they're vaccinated or not, what benefits they get in an entire population that's vaccinated at a certain level. So these concepts, many of which benefit greatly from the use of mathematical models or carefully design field studies. And we've written a book on design analysis of vaccine studies, but it has a lot of epidemic theory and a lot of modeling as well. I just wanted to mention that. So let's, what happened 20 years ago, at least for me, when I arrived here. And it was, as I said, an extremely important part of my development. And I developed a model which I want to just briefly go through during that time. And the model was published a couple of years later in 1996 in the Journal of the Royal Statistical Society C, called a Frailty Mixture Model for Estimating Vaccine Efficacy by Betts and myself. And you can see in the acknowledgments, we acknowledge various NIH grants, but also the Newton Institute. So I thought it'd be good to go through that model a bit for historical continuity, if nothing else. Okay, the basic idea, and this is true for all these models, is that we're concerned with the hazard of infection for somebody in some population. And that's a function of the contact rate times the per contact transmission probability, and then the probability that contact with an infected person at time p. And many models, that proportion is the number infected, over the number in the entire population. But of course, it can be modeled in many different ways. So there's a dynamic part, and we're concerned about decreasing this force of infection to people who are exposed. And the idea with this comprehensive model that we built back in 1993 was that the force of infection to an unvaccinated person will let 0 indicate an unvaccinated, is some random variable, which I'll describe in a minute, z sub 0, times the contact rate times the transmission probability times the probability of infection given contact, where this is made up of the proportion of people who are unvaccinated and infected at time t and those who are vaccinated and infected at time t. And there's another parameter in here, which we'll talk about in a minute, which is how much the infectiousness of an infected vaccinated person is reduced given that they're vaccinated. And so, and then we have the hazard to a vaccinated person. And this part of it, this hazard, is the same. We pick up another random variable for the fact that they're vaccinated. And then this is a reduction, one reduction in their susceptibility given that they're vaccinated. And so we can write survival functions for nu being a 0 or 1 for unvaccinated and vaccinated people. And that's the expectation of the exponent of the cumulative hazard, as you know from survival analysis, which is a Laplace transform of z. And so we basically have this cumulative hazard to unvaccinated people, and that's given by this expression, and then the hazard function of vaccinated people, cumulative hazard given by this expression. So that's the basic way the model was formulated. And then let's say a little bit about that random variable z. It takes on the probability 0 with this with probability alpha nu for vaccinated and unvaccinated people. So that's the probability somebody is not susceptible at all, and it could be different in vaccinated and unvaccinated people. And then the rest of the mass, the probability, away from 0, is given by some continuous density function. So we have that density function of probability 1 minus alpha. And as you might know, in these frailty models, we can't estimate or even define everything. So we let the expected value of x equal 1 and its variance be delta nu. Then then the expected value of z, that's of the x, that's a random variable for the continuous part of the distribution. The expected value of z is 1 minus alpha, and its variance is given by that. And then the Laplace transform of that random variable z is given by that expression. Oh, I keep forgetting I have it's on here. If we further let x be a gamma distribution with the same scale and shape parameters, 1 over delta, then the Laplace transform of z takes on this simple form, and the survival function looks like that. So that's the, for vaccinated and unvaccinated people at time t, the proportion that are not infected. And in the special case where there's no complete protection for either vaccinated or unvaccinated people, we have this form. And then for the degenerate case, in other words, where there's no variance, where f is a degenerate distribution, the survival function looks like that. And that has a very clear, simple physical interpretation in that the proportion not infected by time t is a proportion fully protected here, and the proportion that are not fully protected, they have this exponent of their cumulative hazard. And so to the unvaccinated, it looks like that, and to the vaccinated, it looks like that. And you can see where that individual level protection comes in right here. And of course, it comes in through the alphas. So the model, had, this is just a little illustration of what the model looks like. And so for unvaccinated people, this is in the case where alpha 0 is at 0.1, so 10% of unvaccinated people are fully protected, and the remainder have this density of their susceptibility. And then let's say we vaccinate, and we increase their overall protection up to 50%, and we reduce their per contact probability of infection for those who are not, for those who are vaccinated compared to those who are not by 50%. We just move the continuous part of the distribution to the left, and the discrete part jumps here. So this is what happens when you vaccinate somebody, according to this model. So the estimate of efficacy against infection pops out very nicely out of this model. So it's 1 minus the, this is the probability that a vaccinated person gets infected per contact, and this is the probability an unvaccinated person gets infected per contact. And this reduces to 1 minus, we just simply have these parameters here. So this tells you when you vaccinate somebody how much you reduce their probability of infection per contact with an infected source. And there's some easy special cases of this. One is where there's no initial protection in the unvaccinated, and so the VES is just 1 minus the proportion of vaccinated people who are still susceptible, or not immune, times the reduction in their probability of infection per contact. And we call this the mixed model. If the vaccine has no effect on all or none protection at all, then the VES is just 1 minus theta, which we call leaky. And if the vaccine only protects against, only raises the level of protection, all or none protection against infection, but has no partial effect, then the VES is just a proportion who are fully protected among the vaccinated. We call that all or none. And as I said, and so this construct for many years has allowed us, not by itself, but has helped us move forward in estimating these vaccine efficacy parameters from field studies and modeling the effects of vaccine. So that's just a little story I wanted to tell as a preamble. Oh, one other thing with respect to inference. This is one example of how you could use this model for inference on group survival data. So we want to estimate all these parameters from some data, and our observations come, we know there are so many cases per interval, so we can write the cumulative hazard function as the summation, and then what we observe in each interval are the number of people at risk at the beginning of each interval among the vaccinated and unvaccinated, and the number infected of those who get infected during each of those intervals. And it's straightforward to write the likelihood down and estimate the parameters. And we've done this in quite a few cases, but I'm not going to talk about inference today, so I'm not going to go through those. Okay. So let me now introduce the example I'm going to work through in some detail for the remainder of this lecture, and that's dengue modeling. Dengue threatens roughly 30% of the planet's population at this point, and that is expanding and has expanded in recent years due to climate change, urbanization, and global transportation. So we built a individual level stochastic model using many of the principles that we've already talked about this morning to do the following things: determine the optimal vaccination strategies. And dengue vaccines are coming, and the current leading candidate is in a phase 3 trial throughout the planet and made by Sanofi at this point. And we're working very carefully with all the entities involved. We want to be able to predict the effectiveness and impact of vaccination strategies, and especially make estimates of that impact for investment cases for dengue vaccine, for example, by the Gavi Alliance. We want to help with statistical analysis of dengue transmission and vaccine efficacy. We want to help design phase 4 studies once the vaccine is licensed for its use for countries that are going to be first introducers of the vaccine, and then for other countries as more and more vaccine becomes available. And at this point, a lot of this has been a modeling exercise. So we, as we said, we have constructed a model, which I'll describe in a little bit of detail as we move through today's lecture. It has very explicit geographic structure and connectivity. It has vector density and movement, biting rates of mosquitoes. it has a natural history of infection of both humans and the vector, and then it takes into account the epidemiology of dengue in the region, the immune profile. And for those of you who don't know dengue, there's 4 serotypes that interact with each other, and people can be infected with up to 4 of those serotypes. And many times the second infection is the most severe. The components of control, as I said, we're really just considering vaccination. And the vaccine efficacy we're interested in against all 4 serotypes. And I mentioned already the VES, protection against infection. We're also interested in protection against, in this case, transmission to mosquitoes from vaccinated people, protection against illness given infection, and then the usual outcome in most field trials, the protection against illness with infection. We've looked at the following strategies, which I'll go through quickly today. Routine vaccination of 2-year-olds, vaccinating 2-year-olds routinely with catch-up in the older age groups, and then various coverage and targeting of the vaccine. And then we're looking at vaccine effectiveness and impact, and the direct overall total indirect effects and herd effects. Okay. So the model, we've built an SEIR model for the humans and an SEI model for the mosquitoes, and then we, of course, link those two. The basic idea is in humans, you have susceptible humans. If they get infected, they go through about a 7 or 8 day incubation period, and then 2 or 3 day infectious incubation period. Then they're infectious for about a week, then they recover or die. And then they return to susceptible status each time until they've been infected with all 4 serotypes, if that's going to happen. The mosquitoes go through, get infected in their salivary glands. They go through about a 8 or 9, 11-day extrinsic incubation period, and then remain infectious for the rest of their life, which isn't very long after 11 days of incubating. So the human model is constructed basically on it's a large bipartite graph constructed on for a population that has households, schools, neighborhoods, and workplaces. And the mosquito population is set up in a similar way. We only follow infected mosquitoes. Before they're infected, we just model them as densities. And they have local movement in these different settings where they can affect humans, mostly homes, households, and schools, workplaces, and occasionally an errant mosquito flies off a long distance. But this particular vector, Aedes aegypti, usually stays within 100 meters of where it was born. We constructed the model for an area in rural Thailand, Ratchaburi, Thailand, where dengue is hyperendemic. And we constructed a synthetic population of 207,000 people with households spatially distributed over a grid. All these results are published in this publication down here in neglected tropical diseases. So basically the grid at which we're simulating on looks like that. We're down to 1 square kilometer resolution. There are 394 schools modeled. Of course, we're also modeling the households. And this just shows in the Ratchaburi, it's a part of a place called Ratchaburi called Bang Pai district, how people are concentrated. Now, when you come in and vaccinate, we know from data that, of course, everybody isn't susceptible, and there's a lot of immunity to all 4 serotypes. And this is kind of gives you the starting point for the modeling, and it shows the proportion of people who are immune as a function of age and to each of the serotypes and to at least one serotype. And so you can see, for example, this is the curve showing the proportion as a function of age who are immune to at least one serotype. We have a lot of immunity in this hyperendemic area. And of course, this shows for each of the serotypes as a function of how they've circulated in past years. So that's basically used as the initial condition for getting the model started. When we fit the model to the data, and I'll show you some runs of the model, we're able to estimate the basic reproductive number for each of the 4 serotypes. And these are the actual stochastic frequencies of what happens when you introduce a single infected, in this case, it's actually a single infected person into a population. And so this shows the distribution, whose mean is the basic reproductive number. And it turns out for serotypes 1 and 3, it's about 5.4, and for serotype 2 and 4, it's 5.1. So this is estimated empirically from the fitted model. And then, but when you put that immune profile I showed you on the population, this shows the effective reproductive number at the beginning of when you'd be introducing vaccine. And you can see it's quite a bit less for each of the serotypes. It's on the order of about 2 or so. Okay, so that's basically telling us we already know we could compute the somewhat complicated situation that it would take about 70% coverage of the entire population to eradicate dengue. So I'm going to show you a simulation now, a realization of just one baseline outbreak in Ratchaburi. So the black shows you the infected humans, and over here in the green are the infected mosquitoes in the population. You can watch them on the geographic space. And then here's the epidemic curve. Black are newly infected people, and red are symptomatic. So it's infection incidence and illness incidence. And you can see it takes quite a long time. It takes about 20. The serial interval for this disease is about 20 days. So it takes quite long for these outbreaks to build. So what about the vaccine? The vaccine, this is Sanofi's vaccine. It's the only one that works. Well, I'm sorry, the only one that's being tested at the moment in phase 3 trials. And it's made from a yellow fever virus. It's just basically reverse genetically engineered. It's a chimeric. And you basically start with a yellow fever virus backbone, and you insert epitopes from all 4 of the dengue serotypes. And you end up with a vaccine that protects against all 4 serotypes, one would hope. However, there was a phase 2B trial. That's an underpowered phase 3 trial run in that same area, Ratchaburi. I just showed you the simulations. And what was estimated from that trial was a VESP. So how much does a vaccine reduce the probability of infection with illness? In this case, it'd be per contact with an infected mosquito over the course of a single epidemic. It was actually over a 2.5-year period. And the crude estimate was about 35%. And this shows you the estimated efficacy against all 4 serotypes from that trial. And this is published in Lancet. And you can see in this particular setting, the vaccine did not work well against serotype 2. So what do we know so far? As I said, we spent a lot of time trying to estimate all these things. Well, we know the VESP. Only 8% of the population have immunologic infection data. So we're busy trying to find correlates and surrogates of protection and efficacy. And we don't really know the VES, VEP, and VEI at this point, but at least for modeling purposes, we know the VESP. And this just shows that in this particular population, about 44% of all the infections were serotype 2, and it translated into a actual, this is not crude, but adjusted efficacy of about 45%. But if there had been no type 2, it would have been close to 80%. And if they were all serotype 2, of course, it would have been very low. So this does not tell us what the efficacy is in general. It just tells us in that particular population. And so in our simulator, we did various simulations. One where you get good protection against all 4 serotypes at the 70% level, and then others where you only get protection at 70% against one of the three of the 4 serotypes and no protection against the other one. And then we looked at overall effectiveness, which I think Bets will talk about a little bit later. But that's the overall reduction in the rate to the vaccinated, in the vaccinated population versus an unvaccinated population. And this, oops, what happened to my, I'm missing a slide. That's okay. This just shows what happens in a single season. This is a simulation I showed you earlier where you do nothing. And this is where you vaccinate 70% of the 2 to 14-year-olds. You get that epidemic curve. And then when you vaccinate, in the model, of course, 70% of the 2 to 46-year-olds. And you're getting very close to eliminating dengue in the simulator. And so this is kind of a summary of what I just showed you. And the overall impact, this just shows the coverage of the targeted population, of the overall population, and the overall reduction in incidence of dengue. So with each of those strategies. Yeah. People wanted to know what would happen if you use this vaccine. It did not protect against different serotypes. And so this shows different coverage levels. When you have 30%, 50%, and 70% coverage, and the vaccine protects against all the serotypes, and you're running about reduction from about 5% incidence down to 2, and then this one is missing serotype 1. It doesn't work against 1, against 2, 3, and 4. So basically, you're getting down, in about a 3% attack rate rather than a 5%, even with the mismatch. And so this is just talking about that issue. Finally, what about many years of vaccination? So this is a simulation now running over 10 years in Rochberry. So we had to add vital dynamics to this already complicated model. And so this just shows 10 years of simulated data. For those of you who've studied dengue, we have the serotypes very well mixed. So in real life, you don't see anything quite this regular, but we wanted to evaluate the worst case scenario. And so this shows 10 years of simulation. And then we looked at various realistic rollout strategies. This is rolling out vaccine over a 3-year period to up to age 14, since you can't vaccinate everybody at the same time. And then this is a more complicated rollout strategy. It takes 9 years to reach all the way up to age 44 in graduated ways. And so this is the kind of strategies that people think that you might actually be able to pull off. And so this final simulation I will try to show you, if I can find, there it is. Shows those 3 strategies: doing nothing, vaccinating in a graduated way up to 14 years of age, and then vaccinating up to 44 years of age. Okay. And you can see the impact. And you can see it takes a while, of course, because things are brought in step by step to have a significant impact on dengue. And this is modeling, again, Rochberry, that particular area. Okay. Okay, so we're not talking about eradication here, but we are talking about, if we could get up into the higher age groups, a significant reduction in cases. Oops. And that's just showing you that result. And this just shows, kind of translating this to other parts of Southeast Asia, what the reduction in the cumulative number of cases and the cumulative number of hospitalizations would be per 100,000 people with these different strategies. So you can see over 10 years, considering 100,000 people at risk, that instead of having 16,394 cumulative ill and hospitalized people, you'd have 5,479. And then if you did the more aggressive program, these are cases averted, I'm sorry, you would avert 5,000 cases and 179 hospitalizations. And here, per 100,000 at risk, you'd avert 7,600 cases and 217 hospitalizations. Okay, so what do we conclude from all this? And as we move forward, that first, and I haven't shown you all the results, but we've shown in many investigations that the first limited quantities of vaccine should be concentrated in children. That cascading introduction of vaccine as it becomes available, reaching 70% of each targeted age group should be an effective control strategy. There always should be routine vaccination of 2-year-olds, and that these rapid catch-up programs into older age groups are absolutely necessary. And so that brings us to the vaccine. And the vaccine that protects only against 3 serotypes could still be effective. Obviously, you'd have to pay attention to where the vaccine was used, but you'd get some reduction. And the basic idea is more studies, both mathematical and in the field, and vaccine studies need to be carried out. And right now, there's a multi-center, the phase 3. Large-scale, real phase 3 trial is in the field with all 4 serotypes in Latin America and Southeast Asia. And we'll have those results by the fourth quarter of 2014. So I want to, as always, thank our funders, because we couldn't do this without them. And thank you for your patience.
And speak loudly.
Sure. Hey, Ira, have you considered, so you were looking just at vaccine stuff, but have you framed this in a way that you could combine it with vector control?
Oh, yes.
Okay. Can you talk a little bit about that?
Okay, vector control, since we're explicitly modeling mosquitoes, their densities, and their where and how they bite humans, we can obviously put vector control in very easily. The problem with vector control, at least the classical vector control, is it doesn't work. So kind of simulating something that doesn't work doesn't interest us entirely at this moment. There's things like Wolbachia and other, infecting mosquitoes with bacteria or viruses or genetically, bred mosquitoes that show more promise. And we would be interested in modeling that. And we could model the interaction, vector control plus vaccination, and so there's plans to do all that. I'm sorry to be so negative about vector control, but it's just for dengue, it's been such a failure that I don't know what to do. Yeah.
Could you say a word, Ira, about your assumptions on interactions between strains? Because, as is well known, that affects the incidence of hemorrhagic disease.
Right.
Rather an important cofactor, and whether your vaccine is actually selecting for certain strains.
Yeah. So in the model, we're assuming if somebody's infected, they have, at the time we built this model, we know a little bit more now, that they have a 1-year cross immunity against all the other strains, and then they're immune to that strain, and then after a year and a half, depending on the distribution, they become susceptible to the other strains. We're assuming the vaccine protects on a one-by-one basis at those efficacies I showed you, like from the phase 2b, against individual strains, and they don't provide any cross immunity, though. As you saw from that failure, it looks like there may be a real cross immunity protection with that vaccine. We have we're in a consortium with Sanofi. It's us, Neil Ferguson's group, and Derek Cummings' group at Hopkins, to try to understand better all these immune interactions, both in the phase 2B, phase 1 and 2, and the coming phase 3. Because I completely agree with you, this cross immunity interaction of the 4 serotypes is extremely important. Yeah.
Perhaps on the same line of questioning, how long does it take for these various strains to develop resistance against the vaccine, since you look at long time periods?
Well, at least we don't know about whether the vaccine will wane or not, or if there'll be resistance. But at least for natural immunity, infection is durable and lifelong against each serotype, or it appears to be. The immunity of this disease is extremely complex. It's very, very difficult to say absolutes about something like dengue. But it appears, and one dengue expert named Scott Halstead said he fell off his chair when he saw the results from this vaccine trial, because the immune response against all 4 serotypes was excellent for this vaccine. And we know there's short-term cross-protection. So why it would fail completely against one of the serotypes when you had a strong immune response against that one and all the others is a complete mystery.
Hi, so I've got 2 questions. One is specific and one more general. So the specific one was, so you estimated the basic reproduction number to be about 5-ish or something like that. And then you put in the background level of pre-existing immunity, and then estimated the reproduction number to be about 2. I'd expect it to be about 1, because you've then just taken out all the susceptibles, or the necessary susceptibles. I didn't understand that bit. And then my more general question was, can this vaccine or these vaccines make things worse, particularly in lower endemicity areas, and have you explored that?
What's your second question again?
Is the use of these vaccines, could these vaccines actually make things worse in the sense that because you pre-immunize the population, and then they get severe disease?
Okay. So answer to the first one, I think, as I said, we have all these serotypes running around, and we're altering the dynamics. And it's a dynamic model, so, I don't think you can just do a simple calculation and say, how much would the effective reproductive number be? It's a very complicated calculation, and so he did it by simulation, and that's how it comes out. It makes intuitive sense to me because remember, you've got all these age groups, you have all these 4 serotypes interacting. With that immune profile, let's see if I can go back to that really quickly. Okay. The force of infection is much higher down here than it is out here, and so maybe about the very young children who are getting most of the cases are coming from the very young children who have a lot of susceptibility, and maybe about only about 20% of them are immune to at least, that's just to one serotype. I mean, any serotype. So, it's not surprising that the reproductive number would be cut roughly in half in a population that looks like this versus one that had no immunity. It's just simply because there's so much higher force of infection to the younger age groups. In answer to your second question, the vaccine could make things worse in populations that don't have a lot of transmission, simply because you'd be postponing the big epidemics, and when they come, they could be quite large. you know. And so we haven't simulated, the only real situation we simulate is this hyperendemic situation where clearly the vaccine would have a major beneficial impact. But more work needs to be done on the, in populations with low intensity of transmission, and to make sure vaccination would be useful, and or that it could possibly make things worse, and we need to investigate that. Yeah.
Thanks. We'll move on to the next speaker.